Welcome back. This week we're going to be looking at Chapter 25, Galaxies and Dark Matter, and then we'll do Chapter 26 on Cosmology. So a few weeks ago, I talked about dark matter galaxial halos, and this was introduced, I believe, in Chapter 23. Now, how do we know that other galaxies besides the Milky Way have dark matter halos? And one of the things that we can do is we can plot the distance from the galactic center on the x-axis, and we can plot rotational speed on the y-axis for any particular galaxy that we happen to observe. And we're going to get, if we do that, we're going to get a plot that looks sort of like this. So this is distance. If we're looking at Newtonian equations, this would be r, and this would be the rotational speed over here, and this would be our velocity. And we know that the velocity is equal to, this is from Newton's laws, we know that the velocity is equal to gm over r. The square of the velocity is, that's the square root of gm over r. The square of the velocity is gm over r. And then we can rearrange this to actually find that mass then is therefore going to be equal to v squared times r divided by g. So we know this is something that we can determine. This is something that we can determine. This is a constant, we know that. And from that we can get a value for mass. And when we do that, we always find out that the mass that we actually derive from this equation is much greater than the mass that we get from other sources. When we try to add up all of the visible mass that we can see in the universe, we get a very, very small percentage, somewhere around 4.6, 5%, 4 to 5%. Some numbers say 4.6, but somewhere around 4 to maybe, let's say, 5% or so of all the matter that we can actually see, that we can actually visualize, is what we would consider to be normal matter. So where's this missing 95, 96%? So that's the question. And one of the implications here is that there must be matter that we can't see. This is the dark matter. What is it? We don't know. It could be a lot of different things. It could be composed of stellar remnants. It could be exotic particles. Maybe at some point in the universe there's a form of matter that doesn't consist of protons and neutrons. Protons and neutrons, we've already seen, are composed of up and down quarks. Maybe there's matter that's composed of strange and charm quarks, or top and bottom quarks. So we don't really know this, but there could be this other form of matter as well. But even if we take the combined masses of everything that we see into consideration, and then we look at some of these other things that, this, what we believe to be this dark matter, and there's also a lot of intra-clustered gas, this still doesn't account for everything. So we have to look elsewhere for the source of whatever other matter will be in the universe, and we'll talk about that a little bit more, I believe, in the next chapter. So we've got this, what I mentioned before, the intra-clustered gas, and that is a form of dark matter, probably, but again, that doesn't account for all the dark matter that we believe to be in the universe. In hot gas, particles are moving away at the same speed as the rest of the cluster, about 1,000 kilometers per second, and that velocity translates to a temperature of about 40 million kelvins. So this very probably, we're looking very deep into space, this very probably is primordial gas. This is gas that didn't, that was left over from the perhaps from the Big Bang, and it never actually condensed into galaxies. Now, galaxies also collide. We've seen that, and computer models produce objects. If you actually put all these parameters in there, you actually get, from a computer model, you'll get, and there's examples of this in your textbook, you actually see pictures that look very much like real photographs that have been taken by satellites, or even from Earth-based telescopes of galaxies. So we can actually see galaxies in collision. We can put in certain parameters into the computer. It will generate something that looks exactly like what we would expect if two galaxies collided. Sometimes, rather than actually having a collision, we have what we could describe as a close encounter, where the galaxies don't actually pass through one another, but rather than a collision, one galaxy will pass very, very closely to another one. Now, even if you actually have a collision of galaxies, it's very rare for stars to actually collide. They don't usually hit one another. But a galaxy passing through another galaxy can actually cause a shock wave to occur, and that's the increase in pressure that you get through the wave actually is going to catalyze galaxy-wide star formation. So when that happens, we get what's known as a starburst galaxy. So this is an indication of probably of two galaxies actually colliding. But even, as I said, without colliding, one galaxy can pass close enough to another to cause certain kinds of perturbations in the shape of the galaxy or in the actual, what we would say, the normal evolution of the galaxy. So without any interaction at all, the galaxies would evolve slowly and steadily in predictable ways, but the interactions can obviously change the course of the evolution of a galaxy. The kinds of interactions that we have, for instance, we have what are called major-major and major-minor mergers, and there's examples of this in your textbook. But for instance, we know that two spirals interact. That's likely going to lead to an elliptical galaxy. A spiral and a dwarf galaxy, for instance, when they interact, they're going to give you an enhanced or enlarged spiral galaxy. And the minor mergers leave the galaxy type pretty much intact. That is, it doesn't really change the shape of the galaxy. So that enhanced spiral is really an example of a spiral, and then which is a major, and then a minor, the dwarf galaxy. When they interact, you're just going to get an enhanced spiral. But but two spirals, which are both majors, that's a major-major interaction. That's going to result in an elliptical. Black holes at the center of galaxies, this is something else that I wanted to discuss. The Milky Way right now is not currently an active galaxy, and yet we have a black hole at the center of the galaxy. So what that's telling us is that although the black hole is there, it's not producing energy right now, or it's producing relatively little energy, because in order to really get an active galaxy, the black hole has to be consuming stars. And that's not what's happening in Sagittarius star at the center of our galaxy. So we know that every active galaxy that we've looked at so far has a supermassive black hole at its center. And it's very likely that every bright galaxy, even when the ones that aren't active, every bright galaxy, such as our own Milky Way, also have a supermassive black hole. The brightest quasars have black holes that actually are consuming up to 1,000 solar masses per year. And it would take 1 million years to consume 1 billion solar masses at that rate. But what happens is, after a few million years, they would actually run out of fuel. So in order to make supermassive black holes, most likely what actually winds up happening is that smaller black holes would actually have to merge. And there's an example that's given in your textbook, the starburst galaxy NGC 6240. And this probably seems to have resulted from a merger that took place probably something like about 30 million years ago. And there are two black holes in this galaxy. Now, so the galaxies began to merge 30 million years ago. They started to move closer together. But at the rate that the motion is taking place, it's predicted that it's going to take another 40 million years before these two black holes that are approaching one another actually merge to form a much larger supermassive black hole. And so that would take another 40 million years. Black hole masses are also correlated with the mass of the galactic bulge. And this may be, there's a feedback mechanism, it's called quasar feedback, that might have something to do with this. In this mechanism, some of the quasar's energy is absorbed by surrounding galactic gas. And this quasar feedback causes pressure that was actually going to accelerate star formation. And after about 5, maybe up to about maybe 10% maximum of the gas is consumed, then it abruptly stops. So that's the feedback part of this thing. So the largest black holes are in the most massive galaxies. And most luminous nuclei should also reside, as you would expect then, they should also reside in the largest galaxy. And they come about through these mergers, as we said before, and they're ultimately going to form ellipticals. The brightest active galaxies are associated with ellipticals. So if we actually look, and this is shown on page 649 of your textbook, there's a diagram which shows you shows some irregulars, and the irregulars merge, and they will form larger galaxies. There'll be a central black hole in both of these. Now these galaxies can also merge, can further merge, and then you can get a much larger galaxy with a supermassive black hole in the center. And this is actually what we've got here is a quasar. So we can have other quasars. So we can have the merger of two quasars, and when that happens, we're going to get a radio galaxy. I'm not drawing this to scale, but a much larger quasar with these radio lobes coming out of it. And over time, the radio galaxy itself is going to become quiescent, and then you're going to have just a normal elliptical that will actually evolve into. But the quasar could do something else. It could merge with a major-minor merger, an irregular galaxy, another irregular down here. So these two merge now, and then you get a Seyfert galaxy. And this over evolutionary time period, then the Seyfert becomes becomes a normal spiral galaxy. So you can see all this in your textbook. But this is kind of a picture of galactic evolution, or one explanation of galactic evolution. So on a large scale, the universe is mapped by redshift surveys. So this is something else that I wanted to talk about. So when we want to try to get an understanding of what the universe looks like on the largest possible scale, we use these redshift surveys. And what we find is that galaxy clusters, so the universe has some structure to it, even beyond, we know that galaxies form galaxy clusters, but even beyond the galaxy clusters, there's still some more structure to the universe. So galaxy clusters are further clustered together in what are known as superclusters. Galaxies and clusters have a filamentous structure with large voids. Now, if you actually look on page 631, you'll see a redshift survey that was done of a section of the galaxy, and it kind of looks a little bit like this. And you're looking out at all of these galaxy clusters that are occurring, and you see that they've got this kind of filamentous type of structure to them. And when you get out to a certain distance, there's like one very, very long filament that goes across. It looks sort of like that, and that is referred to as the Sloan Great Wall, Sloan survey. And this particular structure is quite large. It's something on the order of, I believe it's 200 megaparsecs this way, and 70 megaparsecs out of the plane of the board. So this is one of the largest structures, or perhaps the largest known structure in the universe. So at least to date, right to this point in time, nothing larger than that has actually been found, but 200 megaparsec structures. So physicists say that this kind of thing, I guess it must have looked to somebody very much like there's also areas that are seem to be almost complete voids. I mean, there might be a galaxy or two scattered in there, but they're not associated with these filaments. And this kind of looks, if you think about it, it sort of looks a little bit like if you were blowing soap bubbles. You'd have a bubble, and then you'd have maybe another bubble on top of that, and another bubble. And it seems as though in the bubble itself, of course, there'd be nothing. This would be a void. And these are voids here. But where these filaments kind of come in contact with one another, that seems to be like along the surface of the bubble. So you've got a bubble and another bubble and another bubble. As these things are expanding, the matter, just as this were a soap bubble, all of the matter, or well, that's not true, all of the matter, because you also have gas in there, but at least the part of it that we associated as being solid, that's all lying right on the surface here, and it's expanding with the surface. So that seems to be what we're seeing in these kinds of redshift surveys. There's also a distant quasar, 5,700 megaparsecs from the Earth, that is designated PHL 938, and this one has an emission line redshift of 1.954. But some of the absorption lines are only shifted by 0.613. And this is believed to be due to the fact that what we're getting, this again is an extraordinarily distant object, but what we're seeing is some light that is coming to us directly from the object, and other light that is actually coming through. If here's our line of sight, here's our eye over here, we're looking at it through here, and this very, very distant object is here. We're seeing this redshifted, but then we're seeing a different redshift for some of the light, because some of the light is passing through gas or whatever it happens to be, and it's getting shifted differently. So we can actually use these differences in shift to kind of extrapolate out here and find out what other objects might be between this very distant object and our line of sight. And what we find is when we plot out all of these emissions, and we can look at the Lyman alpha line. So that's in the region of the electromagnetic spectrum where hydrogen is absorbing energy and is emitting energy in the ultraviolet region of the spectrum. And what we find is that if we look at the Lyman alpha line, we're going to get that some of these lines are going to be like we might see lines out at 564, and then we see a whole, just looks like a lot of noise in here, and then we'll get some bigger lines up here, and they won't be as big as the initial one, but we'll get some other lines that look sort of like that, and this will center in around 122 nanometers. This particular picture is for a quasar that is designated QSO 1422 plus 2309. You don't need to know these, I'm not going to ask you anything like that, but I just wanted to show you. But this kind of picket fence looking thing here is actually all the lines that are in here are from foreground clouds. These could be atomic clouds in here that are in the foreground, and they're all absorbing some of this, some of the radiation, and it's being re-emitted at different wavelengths. So out here, the 122 nanometers, that's in the vacuum ultraviolet region. So this is the actual emission here, and this big peak over here is at 564 nanometers. 564 is actually in the visible. That's probably green or yellow light that's coming out of there. So this has been tremendously shifted. This stuff from the UV, from the vacuum UV, this is a deep UV, is shifted all the way into the visible region of the spectrum. And this is called the Lyman alpha forest. So this thing here. Another very interesting thing having to do with quasars, quasar mirages. And this just vindicates Einstein's theory that a very massive object can bend light. And it can bend light sometimes in some very unusual ways. So actually, if we have a quasar, which is already a pretty distant object. So let's say the quasar is over here, and your eye is over here this time. So we're looking at this, we're looking at the light coming in from the quasar. The quasar is actually located here, but what we actually see are what are known as quasar mirages. So we'll see a quasar, we'll see what appears to be this quasar over here, and then we'll see another one over here. We're not actually seeing the actual quasar because there is it turns out that there is a large galaxy somewhere in between our line of sight and the quasar, and the galaxy itself is actually going to cause a lensing effect, which is actually going to bend light. So the light, the light that's actually coming out of the quasar is actually going to be bent. It sort of goes like that, and then this line here is actually our line of sight. The light is actually bent around here to our eye, and so what we actually see then is the quasar over here. So this is let's say quasar image 2, and here's the actual quasar, and then we have the same thing happening over here. So the light is coming down, and we've also got light rays that are coming this way, and they're also going to be bent back like that. And if we extend this out, we're going to see our other image. So this is quasar image 1, and so we have these quasar mirages. They're not really there, but that's what we see. Well, it turns out there's something very interesting about this, and that's the fact that these paths are not necessarily going to be the same. I mean, they could differ by a considerable amount of distance, depending on how this galaxy happens to be oriented. These things, I've shown this in a more or less symmetrical way, so in the drawing that I've shown you, they seem to be the same, but they don't have to be. It may turn out that this image that we're getting here actually is forming at a closer distance than that image, which means that if something happens to this quasar, if something goes on here, if this thing were to, for instance, blow up or something like that, we would see the light from that in this image first. We'd be able to observe that, and then sometime later we would see this. We would see this second image, which is, say, further away. We'd be able to see the light from that because it's going to take a finite amount of time for the light to move from here to here or from here to there. And this is going to be a longer path length, so it's going to take a little bit longer. This gives astronomers actually a kind of a second look, so to speak, because what they'll see happening here, whatever's going on in the quasar, whatever they observe here, they're going to observe the same thing here at a later point in time. So that's kind of an interesting way of getting a second look. The other thing about this lensing effect, the other thing that it does is it will actually brighten the amount of light that's coming in, and that depends on the size of the emitting region, which is going to depend on the wavelength also that's being emitted. X-rays are emitted, for example, from a smaller region than, for instance, visible light would be. That would actually come out of a larger region. This lensing effect can also result, here I'm showing you something that shows us two images, but there is on page 655 of your textbook, and it's showing a Hubble image where you see a central bright light, and then you see what appears to be around that four images, which might appear as though they were stars or something like that. But this is what's called an Einstein cross. And what it is again, it's this, these are actually mirages here, quasar mirages. And you can get the same, that same kind of effect where you get these multiple images as well. And again, all this has to do with the fact that a large galaxy, a gravitational lens, is actually bending this light from a more distant quasar. You can also have something called galaxy cluster lensing. So you can have clusters of galaxies that are actually going to cause very distant galaxies to appear, rather than seeing a sharp image, you see arcs. So you see these like long kinds of arcs. And I think there's a photo of that as well in your book on page 656. So you can see all these kinds of things, but they all have, they're all part and parcel of the same phenomenon, that is either micro lensing or macro lensing of the light. There is one other thing that I wanted to mention from this chapter, and that has to do with a particularly interesting cluster that is designated IE 0657-56. And again, don't expect you to remember any of these numbers, but this thing is called the bullet cluster. And the bullet cluster is really a very, very good illustration of two colliding galaxies. It also brings us to kind of something that we can use as an illustration of dark matter. Because we're going to talk about, in the next chapter, we're going to talk about also a little bit about dark energy, which is the other kind of missing piece of our universal puzzle. So what we've got here are two red glowing areas. And basically, these are hot gaseous regions here. These are two galaxies actually that are colliding. And what seems to be happening is one is going this way and the other one is going that way. There are outer regions here, which are not really shown because this is kind of an invisible region. But these regions here is where this invisible mass, this is the region where dark matter is going to be in here and here. And dark matter is not interacting with luminous matter, with the normal matter that we are looking at. So again, the dark matter it's not producing any visible light. It doesn't absorb light. So this is stuff that we really can't see. But this material, when the galaxies collide, the gas pressure stop the gaseous regions from moving, but the dark matter continue to move through the gas. So these things actually stop, and it's the dark matter that actually continues to move in this fashion. These regions are beginning to merge. This pressure from the ordinary matter is actually preventing these things. It's slowing these things down. But the dark matter, because it's not interacting with the other matter in here, the dark matter will continue to move through here, and that's what we appear to be seeing in this particular collision. By the way, this thing is quite distant. It's a billion parsecs away, 10 to the third megaparsecs, and it's believed to be of everything that's ever been observed in the universe. This is believed to be the most energetic collision yet outside of the Big Bang itself. So I think that's probably everything that I wanted to say about galaxies and dark matter for the time being. And we still don't really have a good handle on what dark matter is, but what I did want to tell you is that if we took the visible matter that we have in the universe and the dark matter, we still have only something on the order of 27%. So let's say 23% of this is dark matter, and the other 4% was, we'll call it luminous matter, which is ordinary matter. We're still missing almost 3/4 of the mass that we know to be there, but neither dark matter nor normal matter actually can account for it. So we have to look for something else, and that's what we're going to talk about in the next chapter.